Now I am ready. Does anybody need a Laplace table? And keep this and bring it to class. Yeah, I always complain that linear algebra should be a lot more than 3 units. I feel okay with this. I don't feel too rushed in this class. It feels like we're on a good pace. We'll cover the right amount of material in the right amount of time. So I'm not too sad this is a 3-unit class. What do you guys think about it? Okay. Yeah, it feels like a really good class. Yeah. Yeah. Okay. On the test?
I think so, right?
I don't know.
What we supposed to turn everything?
Yeah, in general, whatever's covered on the test, you should turn into the homework. You got your Laplace transforms. Okay, we're going to take next Tuesday off.
What would you say your projection would be for the next exam? So chapter 7 review?
7 review, yeah, that's all the Laplace transforms. We'll get to 8.
Okay.
And did we do anything else? Oh, second order stuff was this time, right? That chapter 4?
Yeah.
So probably 4, 7, and 8.
Oh, so we can do this
Course.
Tuesday off.
Yes,
Is there a holiday?
there is.
When is it?
Teacher Professional
Oh,
Development
right,
Day.
you were saying that, and
Yes.
you were saying that your tender
I'm going to kick back. There's a new Breaking Bad movie, so
is.
download that and watch it. Yeah.
It's a movie, right? It's not a show.
No, just a movie.
Yeah.
So it's Jesse and Skinny Pete and what's the Badger? I guess is the other friend.
Yeah.
They go meet up again. Okay. Let's do some math. And I took everything in chapter 7 and put it in an order that made sense to me, so I'm not even going to try to guess which section each of these are coming out of. By the time I finish my lectures, you'll know everything you need to know about chapter 7. So if you can see this. There we go. If you see a block on a spring with a dash pot and an external force, and I want to focus on this external force, is if I drew the graph of sine, the graph of sine looks like this. But when do we start our experiment? Whereas our experiment is always started at time t equals 0. So it's not like we can be applying the forcing function to the magnet or to the block before we even set it up. So a better way to describe what's happening here is the external force stays off until we turn it on at time 0. So we want to map away the model, keep a sine function, but only turn it on at time 0. So depending on your class, this function that does that for us is either called the Heaviside function or the unit step function. So we make a new function now. Call it u of t. And this is our just basic turning on a switch. So it's 0. I'll just grab some new pens. So our unit step function, there we go, that looks nice, is 0 before we turn on the switch. And it turns into 1 after that. So if I do my unit function times the sine of t, well, at negative times, what's u of t?
0.
0. So 0 times sine of t is 0. And for positive times, what's u of t?
Sine.
Oh, so u is 1,
It's 1.
and this whole thing is sine of t. So this is what I use to model this function. So this just says I can turn it off. Well, this turn on at time 0. We don't have to worry about what happens before time starts. So look at that here. So if I had, make a simpler differential equation. If my forcing function was u of t, what does that represent to you? So at time 0, so before we started the experiment, the magnet wasn't even on. And then at time 0, we turned the magnet on. Is the magnet pulling up or down?
Down.
Down. It's pulling in the positive direction with a force of
1.
1. Right. And remember, our strategy for solving these is to take the Laplace transform of both sides. And what you're probably wondering is, what's the Laplace transform of this guy? And the answer is, I guess there, 1 over s. Could you prove that if you had to?
Yeah, because even the 0 power is going to be 1, right?
Yeah, essentially. Yeah, we have it there. So we can either do it the hard way from using the definition, or it's, well, we should probably talk about this a little bit. Is we do what's called a one-sided Laplace transform or a unilateral Laplace transform if we start at 0. So for the Laplace transform, it didn't matter what happened to the function before 0, whether it was the unit step function or it was the constant function 1. Our Laplace transform is going to be the same. It's sometimes you use the bilateral or the two-sided Laplace transform. So sometimes you go from minus infinity to infinity instead of 0. That seems reasonable. Now, what I want you to imagine is that we want the magnet, we want the forcing function to be a sine curve. But I want to turn that sine curve, that sine wave on at time 2, not at time 0.
Okay, do sine of t plus 2,
Close.
t minus 2.
There you go. So sine t looks like this. And sine of t minus 2 is going to move the whole thing over by 2. But what I really want to do is move this forcing function over by 2. Right, so what we talked about is the one that just stays off until time 0 and then turns on. And this is u of t sine times sine of t. And then if I want to move that entire mess over by 2, is I just, everywhere I see a t in this function, I replace it by t minus 2. So is that okay if I want to shift the entire graph to the right by 2? Just replace all the t's by t minus 2? Yes or no?
Yeah.
Yes? Everybody? Okay. So, same thing. Imagine I've got my setup. So that's the most basic walk on a spring we could have. And this time, we're delaying the forcing function by 2. Take the Laplace transform of both sides. So what do I want to talk about now? So I guess two things. How to do the Laplace transform of, actually, we'll just do it this way. So if I have a function shifted, so in the time domain, I'm just shifting it into the future. And how does that correspond to something in the frequency domain? Oh, there we go. So looking at the chart, is if I have a u of t minus a times f of t minus a, just like we have here, that sine curve, that sine wave that started at time t equals 2. This is the time domain. In the frequency domain, is we've got e to the minus as times the f of s. What does this f of s stand for? So I'm just looking at the chart. It's, I don't know, about 2/3 of the way down.
It is multiplications.
It's multiplication, and this f is the transform of the original function. So, show you how we work this. So on the time side, I've got the function sine of t. And according to the chart, if I move sine of t, if I transform it onto the frequency side, what do I get? And you got the chart there.
Or s squared.
And what's b? So for sine of t, it's 1. So this is 1 over s squared plus 1. So you know this basic transform. And then what we're doing is we're just shifting everything over by 2. So when I do u of t minus 2 times the sine of t minus 2, well, the rule says I do e to the minus as, e to the minus 2s times whatever the transform was for the original function. That's what this fs is doing in the chart. So again, I just have my function and I'm delaying it. Instead of turning on at time 0, I want to turn it on sometime in the future. And I want a little Laplace transform of that. It's just going to be e to the minus 2s times the Laplace transform of the unshifted function. Let's try one of these. So we got a new function. So what's on the right side now is a u of t minus 1. So we've seen things like sine and cosine, e to the t. We've seen a t squared. We've seen lots of stuff here. Laplace transform on both sides. So look at the bottom of your chart, or remember what we did in the last lecture, is to do the Laplace transform of y double prime. You can convert it to this. Laplace transform of y prime converts to this, and we've got that 2 times Laplace of y. I want you to catch up there, and then I want to talk about how to do the Laplace transform of the right-hand side. So is this part okay?
So Laplace transform for the first derivative.
Laplace transform of the first derivative is right here.
Right. Yeah.
Laplace transform of the second derivative is here.
Yeah.
So second derivative minus the first derivative minus 2 times the original function. Okay, and then it's one thing that's new with this lecture is we need the Laplace transform of u of t minus 1. And there should be an entry in the chart that has that for us. Kind of do, right? The closest we've got is u of t minus a times f of t minus a corresponds to e to the minus as f of s. So for the chart, we're going to have a u times a function. So is this u times a function?
No.
It is. What's that function? No, it's constant function 1.
The invisible one that's always there.
Right. So, so this is what I was trying to find. But based on my chart, I've got to have it look like u of t minus a times f of t minus a. I got this part covered. So it must be the missing part here to make it match is just 1.
Yeah, there's one, two, the 2 equations before. There's one for u t minus a.
Where? That's delta. It's not u.
Oh, that it matters?
Yes. Oh, okay. So just so we're clear about this, so there's another part of the chart that has some deltas in it,
Oh.
and those deltas are not u's. Those deltas are new functions that I haven't talked to you about yet. So we will talk about those, just not right now. So I'm trying to match up the u, and for u of t minus 1, it's u of t minus 1 times 1. So when I go over to the frequency side, it's the u of t minus 1 part gets translated as e to the minus s. In this constant function 1, we have that somewhere else. What is the Laplace transform of just 1?
It's 1 over s.
Very good. Yeah, so remember that 1 is a special case of e to the 0 t, which corresponds to 1 over s minus 0, which is 1 over s. again is I told you about a new type of function we haven't seen before. To solve initial value problems, we take the Laplace transform of both sides. And we did the Laplace transform of this, and we had to do a bit of work to extract that out of our table. So the right-hand side is e to the minus s times 1 over s. So do you believe that y of 0 is 0, y prime of 0 is 1, and you could heroically figure out the Laplace transform of y? I'm going to save you the intermediate algebra steps. They're not that interesting. What I finally want to do is work back to what the answer tells you. I did a partial fraction decomposition and got all the pieces for you and ended up with this. One part of the table, e to the as, corresponds to what? I think that's the top line of the table. Is that true?
1 over s minus a.
Right, good. You're still copying it down. Give you a little more time. Do that. So that 1 over s minus a looks suspiciously like this. So right now, we're in the frequency domain. We want to translate back to the a's. Oh, it's linear, so we can just keep the 1/3 in front. And then 1 over s minus 2 corresponds to what in the time domain?
E to the
E to the
s
2t.
minus.
So that's the idea, is after a bunch of algebra and partial fraction decompositions, you get an expression like this, and then we're able to pull it back apart and say what the original function is. This one's going to be similar. So the 2/3 is just a constant. The 1 over s plus 1, back in the time domain, is e to the negative 2. And then, and something else we have on the table, which is what we're talking about right now, is if we multiply by an e to the minus s in the frequency domain, that corresponds to doing something in the time domain. So, what we're also going to use is if we have e to the minus ac, to the t minus a, f of t minus a corresponds to e to the minus as fs. So we've got the minus 1/2 here. The 1 over s part, so if I ignore this part, if if I just look at the 1 over s, 1 over s corresponds to what? Yeah, good. E to the 0 t, or 1. So the 1 over s part corresponds to a 1. And multiplying by this minus s just shifts it forward in time by 1 unit. So it's when I do this, say I have to just do it. So this is going to be, this part corresponds to that shifted, and the 1 over s part corresponds to a 1. This next one is 1/6, just comes along for the ride. It's the 1 over s minus 2 corresponds to what? E to the 2t. And the fact that I used an e to the minus f here, e to the minus s, says that I shifted everything forward in time by 2. So there's an e to the 2t. And how do I indicate that I didn't turn it on until time 2? No, t minus 1.
Oh,
T minus s. Okay, but then it's that e to the 2t is we shifted everything over with the t minus 1. So instead of a 2t, I replaced the t by t minus 1. Just to make sure that you get it, try to do this one for me. I'll tell you what I'm thinking. So I'm going to ignore that 1/3. So I've got a 1 over s plus 1 e to the minus s. So this 1 over s plus 1, move that back to the time domain. What is it?
U of t minus 1.
So that's just e. Oh, this is just e to the minus t. So just this part.
Okay.
Yeah, so if I ignore the a part, is the 1 over s plus 1 becomes an e to the minus t. Okay, and then multiplying by this e in the frequency domain, time shifts this one. So then is the effect of this e to the minus s is to shift it 1 second into the future and move the function 1 second into the future as well. So wherever I saw t before, I replace it by a t minus 1. So this part is a u of t minus 1, e to the negative t minus 1. Yeah. We got one more here. Practice this. So the relevant entries on the table for the one I'm about to do are cosine of bt is b over s squared plus 1. Sine of bt is cosine. That's right. And the one we've been using is u of t minus a f of t minus a corresponds to e to the minus as f. So I'm going to give you a Laplace transform, and then I'm going to give you the frequency version of everything. and you're going to convert it back to the time domain. Yeah, I always get that mixed up. I think you're right. Does that look reasonable? You always think I have it straight, and then I never remember. I agree with you 100%. So, let's imagine we worked on a long problem. And I broke it down. So at the end, I got the Laplace transform of the function I'm looking for is this. And what I'm going to try to do is convert this back into the original. So this one's easy. That 1 over s squared plus 1 corresponds to this line. So what's the b value to make these match? B is 1. So if I go in the frequency domain, it's 1 over s squared plus 1. Translate it back to the time domain, what is it? And I'm going to try to do this. I don't know why it's hard to write out the steps, so I'll try to write my thought process. So my thought process is to first ignore the e part. So when I do s over s squared plus 1, oh, we've got it on the chart over there. So ignoring the e, this translates back into what?
Cosine t.
And then what we did is on the frequency side, we multiplied by e to the minus pi over 4s. And multiplying by this on the frequency side is the time delay on the time side. So don't turn it on until pi over 4 seconds after we started. And time shift the original function here as well. So cosine t minus pi over 4. So this part, what's new tonight, is that. So is that good? So I'm going to call this good for this part. I'm good with this part. I want to make sure you are. If it's something you recognize here already, and then on this side we multiplied by e to the minus as, the effect is to do a time shifting of whatever this was. More things? As we can go the other way. So imagine I do a frequency shift. So we know that 1 over s squared plus 1 corresponds to sine t. So just like before, I replaced all of the t's by t minus 4 that happened on the time side. Here, I'm going to take a Laplace transform and replace all the s's by s minus 2. So if I see something like this, I expect to get something on this side. I'm going to get this the wrong direction. So if we translate the frequency forward by 2, in the time domain, we've multiplied by e to the 2t. And if you wanted to, you could actually derive these. Right? It's the Laplace transform. So do the Laplace transform of this. It's some integral you need to evaluate. You can use Calc 2 technique, specifically integration by parts, and you'll end up
not equally good.
No, that's why I always had to double check. So right, this one's always positive, which tricks me up. But it's positive, not negative. And the general rule is on the frequency side, we made some translation. And the time side is it's the original function times an e to the h. So just imagine it'd be one of these. I did my partial fraction breakdown, and I ended up with one of the terms is s over s squared minus 4s plus 5. Can you factor this and break it down into simpler partial fractions?
Yes. You need to factor the denominator and
Right.
multiply both parts.
So you actually not, the denominator does not factor. So this is, sometimes you can factor, sometimes you can't. This is an irreducible quadratic, so this can't be factored. So what I'm going to do is complete the square. I'm going to break this 5 up as a 4 plus 1. And the s squared minus 4s plus 4 should look familiar. What's that? This is s minus 2 squared plus 1. Take it over here. So does this remind you of an s over s squared plus 1? And then, if I want to do the frequency shift, I replace every s by s minus 2. So my denominator, transform this into an s minus 2 squared. And if I'm replacing every s by s minus 2, so that has to go here like this. So if I had s minus 2 over s minus 2 squared plus 1, because that's the sine of the cosine. So this is the cosine. So this is the cosine of t. Doing a shift like this is, what do I do? So the shift on the frequency side corresponds to what on the time side? So if I had an s minus 2 on the top, I'd be good, right? So if these two matched, I had that s minus 2, I know how to convert that back. But in algebra, what I giveth, I taketh away. Has that changed anything now?
No.
It's not. So this is splits into two fractions. An s minus 2 over s minus 2 squared plus 1. Plus another 2 s minus 2 squared plus 1. This one we've done already. E to the 2t sine of t. And we'll do the other one. So without the shift,
Cosine.
good. Thank you. It is cosine. Yes, it is. So the 2 over s squared plus 1 is 2 cosine t. And when we do the shift, so what's the net effect of this s minus 2 rather s minus 2 squared rather than s squared? Yeah, that's going to give us an e to the 2t times the cosine. Did I switch them again? This one's the cosine? As I was saying, that one's the cosine. And that one's the sine. Thank you. Yes?
What is the 2 for the e to the 2t come from?
It's the shift here. I'm going to focus on this one first. So let me get this right. So 1 over s squared plus 1 corresponds to sine 2. And then if I replace this by s minus 2 squared, what that's going to do on the time side is put an e to the 2t on the top.
Yeah, I'm wondering about the 2 that's prior to the e to the 2t.
Oh, this one?
Yes.
Oh, it's that one.
Just the
It's
coefficient.
not like the table where it's just b over s squared plus.
Oh, b is.
That's not b if this. Oh,
No.
b is 1, you're right. Okay.
It is.
Okay. Thank you.
Let's practice another one of these. So we have to complete the square. So I worked through a long problem. So I ended up with the Laplace transform is this, and we're practicing how to go from the frequency, how to go from the transform back to what the original function must have been. So if you could factor this, you could break it down as two simpler functions. I chose one here that you can't factor. So our technique is we're going to complete the square. So I'm going to break that plus 5 down into a plus 1 and plus 4. Because I'm thinking s squared minus 2s. The best way to complete that is a plus 1. Does anybody want to talk about completing the square part? How to break the 5 to 1 and 4? So this is 1 over s minus 1 squared plus 4. Let me think about this a little bit. So this reminds me of, I guess, the 1 over s squared plus b squared. No, the b over s squared plus b squared. So that side? Good. You notice here, I've got 1 over f squared plus 4. What do I wish the denominator was to make this work?
S squared plus 1.
No. I want, if I have a b squared at the bottom, I want the b on the top. So what do I wish the denominator was here? What do I want?
2.
Right. So the form is, right, it's s squared plus b squared on the bottom. I want the top to be the b. So if b squared is 4, what's the b? 2. Very good. So I wish I had a 2 on the top. What I giveth, I taketh away. So I want a 2 there, I'll just put it there. I just have to make sure that I take away whatever I added. So then when I have this gives me a 1/2 sine of 2.
What do you put with that?
So if I'm matching this form, if the bottom is b squared here, I want a b on the top. Who asked that? So it's when I see this, I want a b squared and a b. So if this is a 4 here, I want a 2 on the top. But I only had a 1. So I need to break it. I need to manipulate this a bit, put a 2 here. So if I cross out the 1 and put a 2, and multiply by a half in front, I haven't changed anything. So do you agree that if I do 1/2 times 2 here, those would cancel out to be the original one that I had?
So you're trying to cancel it.
And I'm trying to build it so this matches that form.
So we sign.
So that would be the sine 2t, and then I still have to have the half in front, cancel out the 2 that I needed to put there. So for this one, I have to put the 2 here and the 1/2 there to make those work out. So without the shift, it's 1/2 times the sine 2t. And this shift in the frequency domain does what in the time domain? Let me show you one of my favorite functions. This is where we're going to get into the deltas. Oh, anybody do machine learning here? Does that sound familiar at all? Okay, never mind.
Why?
Oh, because the U function is related to machine learning. So, yeah, they use the integral of the U function. And they do it when they're training neural nets.
Wow.
I was thinking, like, when you were originally doing that, that it reminded me of, like, the coding portions of, like, some computer science class.
That I believe.
Yeah.
It's all, at some deep level, we're all just pulling from the same small box of tools. It's all related. Okay. Yeah.
You get easy from 1 over s minus 1.
The s minus 1. So if I just had 2 over s squared plus 4, we said over there that corresponds to the sine of 2t. And then what the only difference here, instead of the s squared, I've got s minus 1 squared. So it's this minus 1 here that gives me the e to the t here. New function. This is either the Dirac delta function or just the delta function. And we define it to be the derivative of the u function. So let's sketch a graph of this. And I always like to do my derivatives below the original. So there's the u function, right? And what's the derivative of the u function right here? What's the slope of this curve? Here? Here? What about over here? So it's going to be 0. So it's going to be 0 all through here. And it's going to be 0 everywhere else. But yet, what's the slope here, right at this point when I make the jump?
Undefined.
It's undefined. And so it's undefined because it's a vertical line. Right? You see if I'm doing those tangent approximations, get a vertical line. So the way we represent that is we put just a big spike here, and I decorate that with a 1. You don't really know how tall it goes. So the 1 indicates that it came from, it's 1 times the derivative of that. This is, you can see delta is not really a function. So what happened was the physicists, led by Dirac, said, let's pretend it's a function and we'll do all our calculations with it. And they always got the right answer and it was interesting. The mathematicians hated it, the physicists like it. And then eventually, its mathematicians figured out what's going on in the mathematical sense. But for now, this will just be physicists. Let me tell you a little bit about some things about this function. So if I'm integrating this function, it's, well, what the delta is the derivative of the u function. So this would be u of v minus u of a. And if I always if a and b were on the same side of the 0, then the u would be the same. But if I started the a over here and ended it here, so if we do a is less than 0 and b is positive, what's u of b? So if b is a number over here, what's the output of the unit step function with the positive number? 1. And the output of the unit step function? 0. And the way we usually write that so somehow it's this function that's 0 everywhere except at this one weird spike. And if we integrate over the entire line, it's the spike lets it integrate to 1. And then, what we call the sifting property. So this is an important function, and I wish we talked a bit more about it. So if I do the Dirac delta function times a given function, now watch what happens here. So if I do that delta t times the f t, oh, what f was at -1 or -7 or 14 isn't going to matter because the delta function is 0 there. So the delta function times f is going to be the same as the delta function times the value at 0. Believe that? So if t is some other number, let's say t is 3. Well, what's delta of 3? 1. What is it? No, delta?
0.
Right. So if I plug a 3 in, so it'll be 0 times f of 3. And what happens if I plug a t equals 3 in here? It'll be 0 again, right? So any t value I pick that's not 0, the delta is going to make this side 0, and the delta is going to make this side 0. So the only way it might possibly be different is what happens at 0. So if I integrate from minus infinity to infinity of delta t times f of t, delta t times f of t is the same thing as delta t times f of 0. And f of 0 is a constant. And what happens if I integrate delta from minus infinity to infinity? 1. So this whole thing is f of 0. So, which you're probably interested in is, oh, actually a couple of things. Let me set up the equation. Let me tell you what it means, and we'll start doing Laplace stuff. Let's look at this differential equation. Does the left side look like a block on a spring? Mass is 1, spring constant is 1. That's your x's. So at time 0, it's at rest, it's not moving, and the forcing function we're applying is the delta function. So remember, the graph of the delta function looks like this. So what this represents is applying an instantaneous force just at time 0. So this would be like we took the block and just hit it with a hammer at time 0 and try to see what happens. So in this context, this is also called an impulse function. So it's just where we do one instantaneous shock to the system, and then it's going to see what the effects are after that. So to solve this, you need to know the Laplace transform of the delta function. And it's on the chart there. So what's the Laplace transform of the delta function? It's 1. And we talked about this part already.
E to the negative.
E to the negative.
AS.
So what does this mean? Instead of delta of t, if it's delta of t minus a, what does this t minus a represent in the time domain?
Shift.
It's a
After.
good shift by a. So instead of doing our impulse at time 0, we do our impulse at time a. So let's try this. Well, actually, what would you expect? So it starts, let's try to guess, and then we'll use the Laplace transform to verify it for us. So before we start the clock, nothing happens. And then if I have my block on a spring, it's not moving, spring is not stretched, and I hit it with a hammer, what's it going to do? It's going to start going down, and then it's going to keep oscillating like this. So I expect the graph to be something like that. And actually, be careful. So the nice thing is we're using one-sided Laplace transforms, so we really can't say anything about what happens before we start the experiment. So x double prime plus x is the impulse function. Laplace both sides. Last time we practiced this is s squared plus y plus s times, or minus s times y of 0 0 minus y prime of 0 plus Laplace transform 1. And what's new in this problem is what's the Laplace transform of the impulse function? Either we just talked about it or it's on the chart. It is 1. So this is me doing the Laplace transform of the left-hand side, and the Laplace transform of the delta function is 1. Oops. These are all x's. I set it up so there was the spring was not stretched originally, and it wasn't moving. It wasn't moving at all. So we get s squared times the Laplace transform of x plus the Laplace transform of x is 1. Factor out the Laplace transform. Laplace transform times s squared plus 1 is 1. That means Laplace transform of x is 1 over s squared plus 1. So in the frequency domain, I get 1 over s squared plus 1. Translate that back to the time domain. I'm going to get it wrong. What is it? It's sine. The solution, the function that describes those oscillations is the sine, which we expect. Let's try one more to practice with this. Remember, we can only use Laplace transforms for initial value problems. So not only do I have to get the whole thing set up for you, but I have to tell you what the initial position is and the initial velocity. All carefully chosen. That's what it came down to. S plus 2. I did all the partial fraction stuff for you. S plus 2 over s squared plus 2s plus 26. And then plus e to the minus 4s over 1 over s squared plus 2s plus 26. Let's try take apart that first one. When I see an s squared plus 2s, what's the obvious thing to make it a perfect square? S squared plus 2s plus
1.
So I'm going to split that 26 into a 1 and a 25. And this is s plus 2, s plus 1 squared plus 25. so I think the basic pieces I'm going to be using are s over s squared plus 25 and 5 over s squared plus 25. Those seem like the ones that are going to be look like an s squared plus 25 on the bottom.
Sine or cosine?
Yeah, good. Yeah, so I guess, yeah, so it's, let me tell you what I see, is I'm focusing on the denominator here.
On the right, you have B, and on the left, you have S.
Right. Yep, that's right. So I see this as my denominator, and this looks like a frequency shifted version of s squared plus 25. So I'm going to do what the over s squared plus 25 first, and then I shift it once in this direction.
How do we have S and 5?
Okay, so first of all, do you believe that it's, I want to start with this denominator and do a frequency shift? So,
Or does 5 replace this? Is that what you're saying?
no. So, it's the denominator, is the basic form of the denominator here is s squared plus b squared. And in particular, I've got s squared plus 5 squared or s squared plus 25. So the two identities that have denominator of s squared plus b squared are, look on the table, what are the numerators?
S.
So one of those is s, and what's the other numerator? B. So for my particular example, when I have a plus 25 here, I want to have an s over s squared plus 25 and a 5 over s squared plus 25. So for this particular 25, these are what I want the numerators to look like. Yeah. Where does all the work go? Yeah, I might regret that. Yeah, I think it is good. So when I have an s over s squared plus 25, what's that going to correspond to? That is cosine of what? 5. And when I have a 5 over s squared plus 25, what does that one correspond to? That's now, it's, I need to massage my s plus 2. Oh, actually, okay, now I guess, yeah, let's do the shifts now. So instead of an s squared plus 25, I've got an s plus 1 squared times 25. So s plus 1 over s plus 1 squared plus 25. So I just took, everywhere I saw an s here, I replaced it by an s plus 1. So what's that going to do to this cosine?
E to the negative 5s.
No. It's this plus 1
Negative.
tells me it's an e to the t.
I was there.
Yeah, me too. That's why we have the chart. And the second one, instead of making it a 5 over s squared plus 25, I'll make it 5 over s plus 1 squared times 25. So replacing, keeping everything else the same, but replacing the s by an s plus 1 does what in the time domain? Yeah, the time domain. I take that e sine 5t, and what happens to this part? That's an e.
So no matter what,
It should be a
It is?
Yeah. Yeah.
Are you sure?
S minus
Yep.
Yeah. That's mine.
Oh, it's S minus. Yeah, that I agree with.
Yeah, 'cause
That's why we have a chart. You guys are right. Yeah, you're right. Okay. So it's this first part, this S plus 2 over S squared plus 2S plus 26. I'm going to somehow algebraically manipulate it to get pieces that look like each of these.
I think we're missing the coefficient in e to the negative t. That there should be a coefficient because we start with 2 over whatever's on the bottom. So we need to multiply it by
1/5.
Multiply 1/5. Yes, here.
No. Because remember, it's the transformation is if I have b over s squared plus b squared. Notice the b squared down here and the b on the top.
Right.
So if it's a 25 down here, I need 5 on the top.
Yeah, but you
But
didn't have
actually
the five.
it's S
Oh, no.
plus 2, so
You had 2 initially.
Oh, hold on.
Oh.
Okay, so do you believe that if I see one of these, it transforms to this?
Right.
And if I see one of these, it transforms to that.
Right.
Okay, so what I'm going to do is try to manipulate this into 2 pieces, one piece of this form and one piece of that form. So these are just the base transformations that I'm going to try to massage this into.
So the other steps are coming.
Yeah, we're getting there. So I've got this guy, which I'm going to write as s plus 2 over s plus 1 squared plus 25. Right? Okay. And for the cosine transformation, what do I want the numerator to be?
It's 5.
No, for the cosine transformation,
S.
Oh,
It's already there.
X plus 1.
I want it to be s plus 1.
Would become S plus 1 plus 1.
Good. So does everybody see that in order to use this guy, I need this s plus 1 squared to match the s plus 1 there. So what this is, I'm going to split this up into an s plus 1, s plus 1 squared plus 25, plus what's left over?
1.
1 over s plus 1 squared plus 25. And I'm happy with the numerator here. And you were getting ahead of me. What do I want the numerator for this one to be?
5.
I want it to be 5. So I'll just do what I like to do with algebra. Put a 5 there.
You have to divide it.
And then I have to put a 1/5 on the outside in order to pay for that. So this part translates, we worked it out over there, e to the minus t cosine 5t. And this part translates to 1/5 e to the minus t 5t. Translate, I'm gonna rewrite all of this over here now. So the 2 pieces of the puzzle were s plus 2 over s, sorry, it was s plus 1. No. We had s plus 2 over s squared plus 2s plus 26 plus e to the minus 4s 1 s squared plus 2s plus 26. In this part, we just translated the e to the minus t cosine 5t plus 1/5 e to the minus t sine 5t. So far, so good? We have to do this guy. So that's 1 over s plus 1 squared plus 25. That's not bad. What do I wish the numerator was? So I wish it was a 5. And I'm not too sad when that happens. I can make it a 5, put a 1/5 out there. So when I have this part, I get 1/5. Is this the sign?
Sine.
Yes, it is.
Sine 5t.
Right? So, it's, I know the part without the E.
It's basically time.
Okay, I'll finish this up. Less than. So without the E, I get 1/5 sine of 5t. And then we talked about this at the beginning of the lecture. If I multiply by an e to the minus 4s in the frequency domain, how does that translate? What happened in the time domain? Yeah, that's a u. So this translates to a u of t minus 4. And I have to translate it's the original function by t minus 4 as well. So the second piece of the puzzle here is a u of t minus 4 times sine of 5 t minus 4. So that's the original equation, but we had an original setup. We had a damped system that was, it started with, we stretched the spring by a little bit. It started oscillating the system. And then a couple seconds later, we hit the thing with the hammer, and that's going to change. So 4 seconds later, we're going to have the initial oscillations that are decaying, plus the hammer hit right here.
Is it possible to solve problems like this with undetermined coefficients?
Except we don't know how to deal with deltas. So we don't know if we make our UC set with the delta, we don't know what it does. Okay, so I guess I'm over time. Say Tuesday or Thursday? Tuesday? Today's Tuesday, so I'll see you on Thursday. And then it's next week that we're not going to have class.
Thank you.
What did I miss? It's right here.
No, the last first.
Yes, I did. Not anymore. Thank you.
You really can talk there.
Oh, I know, yeah. I'm worried more about this, but you're right, yeah, there's a lot of little details that we need to keep track of. In the frequency domain, yeah. By the way, we haven't really talked about what happened on the S side yet. So just think, I'll have my here, replace the S by S.